Good afternoon, it's me again, Jean-Louis Vimbella. I'm an amateur physicist. I've got quite a lot of videos and publications that are going quite well, but yeah, they're not mainstream. If you go on my YouTube site, you will see them. That sort of, things amount a bit to a reinvention of the sector of quantum electrodynamics. I will just show this one. The Broglie's matter wave now has about 15,000 reads. Basically, this paper sets a sort of basis for reinterpreting quantum electrodynamics in the sense that it's a very simple hypothesis. Instead of thinking of matter particles as their energy and they have a frequency. It's some oscillation, but matter particles stay where they are. And so in this paper, I explore a hypothesis that basically said, instead of what I think de Broglie's mistake was, is if you think of frequencies and oscillations, you should not necessarily think of a linear oscillation like a light wave or a light particle. Think of orbital oscillations, charges going round and round and round. And that works really well and sort of explains a lot of stuff. The thing is, and that's what I want to do with and highlight a bit in this video is I've started to write a bit on this field of quantum chromodynamics, as I would say, but I call it high energy physics. What happens inside of a nucleus and things. And that's where I have a series of papers which I haven't really. I will show a few of them in a moment, which sort of also deconstruct the sector of quantum chromodynamics, I would say, or high energy physics, or actually the whole quark gluon theory. The idea that there are, besides electric charges, something like, a strong charge or, a weak force. I think everything is electromagnetic. But yeah, electromagnetism is, it's a force which you should analyze in terms of bivectors. And, when you talk about two charges, it's fairly easy, but, two charges close to each other, opposite charges make a dipole. So the field looks different, and that's what I want to talk a little bit about. This idea of the current quantum field theory and interactions that work through an exchange of virtual particles. Where did it come from, and how sound is it? I write here quite bluntly. The idea of a strong force, I do not find it very sensical, and that's why despite all the Nobel Prizes that have been awarded to these new theories, I don't buy them, and I want to go back, as I did in a few other papers, to sort of the origins of the idea. So I'm going to explain what Yukawa came up with in 1935, a theory of a strong interaction to explain why, a proton and a neutron would stick together, or a proton and a proton, despite opposite electric charge, seem to stick together. On that thing, let me immediately tell you that, proton and a proton in a nucleus, you don't find that combination. It will always be a proton and another proton and neutron. So this is the thing, the neutron acts as a kind of glue, obviously. And if you interpret a neutron as, some kind of combination of positive and negative charge in that theory that I have, where, these matter particles, elementary matter particles should be, charged in oscillations or charged oscillations, as I call it, then you can come up with a theory that is based on electromagnetism, which would explain that. It's not an easy one, but it's a much more plausible one than, I would say, the one that Yukawa came up with, despite again that this is a Nobel Prize winning theorist. The formulas I'm going to present, they come out of a serious textbook, Gauged Theories in Particle Physics from Aitchison and Hay, and it comes from chapter 1, which is the foundational chapter, I would say. Particle interactions in the Standard Model is the title. And yeah, it gives you the theoretical model, and I will quote a few things out of it. So let's go to Yukawa, 1935. What was his theory, basically? He said, two protons, or proton and neutron, they should repel each other because of their electric charge. So we should think of a force that is opposite first. And, because what we see is this force also only comes into play in a nucleus, so it acts only at a very, very short distance. So we should think of a force which decreases much more rapidly than here. Oops, sorry. Let me do that again. Which decreases much more rapidly than the inverse square law that we know so well. The inverse square law comes out of electrostatics. So I put a reminder there a little bit in terms of formulas. The electrostatic force. The electric force here, electrostatic force, is given by this formula. So if we have two charges, Q1 and Q2, the force then will be determined by the magnitude of those two charges, respectively, and will indeed decrease as a function of the inverse square of the distance. Well, the square of the inverse distance. And we multiply that with the electric constant Ke, which is equal to 1 divided by 4 pi, and the electric permittivity. The 4 pi is there because it's spherical radial force, symmetric in all three dimensions of space. So we can associate that with an electric potential. Like stress potential and potential energy are two concepts that are often, confused or mixed. They are strongly related, and often I forget to mention potential energy rather than potential. But let's, for the discussion, be clear about, if we have one charge only, a point charge of so much and so much Coulomb, a Q, the potential will be will fall off. There will be a potential field around it, depending on the sign of the charge, positive or negative, and it will fall off following being proportional with 1 over r, not over 1 squared. That's the difference between potential and a force. How do you get there? That you can look up at standard textbooks. It's the result from an integration. You imagine a unit charge far away at an infinite distance, and you bring that nearer to that charge that we are discussing here, and then you'll see if the charges are opposite. Of course, the potential energy will be negative and positive the other way around. So that's the formula for the potential. Of course, if we replace it, usually we want to think in terms of the unit charge, right? The charge that we have in an electron or proton, QE. Then we have the potential for the unit charge. If we put a unit charge somewhere in space, then the potential of that unit charge will decrease with 1 over r. And again, here we have the electric constant. So that's kind of sensical. Again, when we talk about energy, we're talking about two charges. The energy between the potential energy between two charges. So if we think about the potential energy between two unit charges, then we have QE squared, but we have the same 1 over r law. So that's kind of obvious. And so what Yukawa did is saying basically let's imagine some kind of nuclear potential, UN, right? And then so I have that here. We have the electric potential. If it would be electric, UE, which depends on the distance, 1 over 4 pi times the electric constant here, QE squared divided by r. And he says, I need a potential which falls off much more rapidly, which decreases much more rapidly than that electric potential, a nuclear potential. So he writes, then he replaces QE squared by sort of a nuclear charge squared. And because the force should be opposite, the potential will be opposite as well. He puts a similar thing as 1 divided by 4 pi times epsilon. He writes 1 divided by 4 pi epsilon. In fact, the epsilon I added because you need something to make the units come out right. Epsilon in Yukawa's formula is actually not there. He assumes it's equal to 1, I guess, which is probably linked to this very special functional form he takes instead of 1 over r. He takes 1 over r and he multiplies it by a decreasing exponential function. Let me clean up my sheet. So, yeah, that's a theory. I explored that theory because, and I immediately find that there are a lot of things that sort of make sense, and but more things that don't make sense. The first thing that doesn't make sense is that it doesn't really solve the problem of a force that would decrease with the distance, and then another force that goes like this. And then somehow the two forces are opposite and they keep each other in balance, a nuclear force and electric balance. The thing is, these potentials also associated with the force, at some point in time, they should cross. So if we make abstraction, we should have something like this, perhaps, right? Something that goes to 0 very quickly, but close to with a close distance. This is the scaling factor A. This nuclear force becomes very, very strong, and so the potential also is huge. And then, but at some point in time, this electric and nuclear potential, they should cross, right? And that's the thing with this distance function that he has here. Euler's number to a negative power minus r over a. And 1 over r, if you look at those functions, you can graph it out. These potential functions never cross. See, I put here 1 over x, and then Euler's number to the power minus x over a times that 1 over x factor. And you see the red and the purple, these potentials never cross. So you never actually have, his model doesn't explain, can't explain why, we would have indeed something that would have a functional shape that explains why, two protons would effectively stick together. The other thing is actually with a potential like this, you have this thing is symmetrical in space, but because it does not obey the 1 over r square law, it violates the energy conservation law. I will not talk too much about that, but you can read standard textbooks like Feynman on the law of Gauss in electromagnetics, and that explains that you really need an inverse square law to make sure that you don't have a violation of the energy conservation law. When energy radiates out, light energy or potential, and you move out in space, you can't have a loss of energy when you do that. And here in this formula, you have that. And this brings me to another remark where, this function, now I'm gonna perhaps show my paper. Well, the paper that inspired me a little bit is this one from Paolo Di Sia. He's like a polymath, an Italian polymath. It's a bit of an obscure journal, but it's on ResearchGate, and that's where I found it. I mean, a friend gave it to me. He says, well, if you want to have a law like that, you could sort of imagine a dipole field, indeed, where proton and neutron would have positive and negative charge, and they cancel out, so that makes the neutron neutral. But yeah, they're very strong dipole moments, and we have a similar formula as the one that Yukawa postulates for this nuclear force. And you know, the orders of magnitude, that's the nice thing about that paper from the CIA, is you know, comes out all right. So that's where I'm going, like you know, this is a much more natural theory, and also um, goes back a little bit to what Schrödinger once suggested in terms of what might be going on in a nucleus, Platzwechsel model, where a proton and neutron, you know, exchange a positive charge, and the neutron becomes a proton, and the proton becomes neutron. These kind of things that are just based on plain electric charge. So yeah, and that's the thing where you know, the other paper I do here is I do a physical dimension. That's where I said, you know, you can't just scrap the equivalent. If you put something, write down something like that, you know, nuclear potential, you need a constant, and might be one. We might change the functional forms, go to another basis, and then this epsilon instead of an epsilon would take on another numerical value, but the units need to come out all right. So you do need, when you sort of introduce a nuclear charge, you need to say, well, I have a new unit, a nuclear charge instead of electric charge, which is expressed in Coulomb. You know, we would have to invent, you know, the Dirac, or one Einstein, or I don't know which unit or one Yukawa. You know, you just invent a new unit when you write something like down. When you posit a new force, a force must act on a charge. Just like this, you know, we have color charges and whatever, which I don't believe in. But you know, yeah, you must define a unit, a new unit for the charge. So it could Dirac or the Einstein, or and this is then where I had a lot of fun thinking that through. Let me clean up my sheet again. Is I actually did that in. Let me see which one here. No, no. Yeah, here, where I sort of, you know, I put that formula here, if you see it, Yukawa's nuclear potential and force. And let's make sure we're going to see. Yeah, it's tipping here because I've got two screens. I do say then, yeah, okay, we have a formula that is quite similar to the, you know, for the nuclear, for this nuclear potential and for the electric potential, except for that, you know, yeah, electric constant, we have some kind of nuclear constant. And then I go about saying like, okay, let's invent some kind of Yukawa, the y I put it here, instead of the electric constant, which is expressed in Coulomb squared divided by Newton meter squared. I write then, you know, we have Yukawa squared divided by Newton meter squared. So then, you know, it does the trick. It makes the units come all right. And so, yeah, it would be a big mistake to leave something like that out when you do a physical rather than purely a mathematical formula. Now the thing is, when you fix the dimensions, that's what I put here. Then, sort of, what numerical value should we then take? So we can have the 4 pi, but the 4 pi is just, you know, the formulas that we have for a surface area or the volume of a sphere. So that 4 pi is just is not a miracle. And then, but then the funny thing is, yeah, this distance a. At that distance a, the scaling parameter, the idea is that the nuclear force, this nuclear force, would be equal and opposite to the electrostatic force between the two nuclear components, the proton and neutron or the electron. And then it's sort of, you know, you calculate, say, okay, I'm going to calculate the force, but I said, the funny thing is, the potentials don't cross and the forces don't cross either. When you try to calculate the distance, you don't get a value, and you know, you approach the problem mathematically, which I do here, is sort of, okay, what would be the condition for the nuclear and electrostatic forces to be equal and opposite, and then you arrive at a nonsensical mathematical condition where basically, you know, 2 divided by Euler's number would be 0.7 something, and so that clearly isn't the case, and it's because the formula Doesn't make sense. I said that when you plot the functions, they never cross. So the funny thing is also in this derivation to sort of make sure I need to make some assumptions about the unit of that nuclear charge, the Yukawa, and I arrive actually at a formula which is nothing else, which I say here, Van Balle's formula, uh, which is the electric constant is the unit charge squared divided by 2 times the fine structure constant times Planck's quantum of action and speed of light. So actually, my subcondition to arrive at a condition which would make Yukawa's solution for to explain why two protons stay together and nucleus appear is just a basically sensical definition that we get out of the SI system of units since 2019. And that's the thing I want to conclude with. When you do a physical dimensional analysis of Yukawa's formula, it just does not make sense, and it's not consistent with the 2019 revision of SI units. We do not have, a separate nuclear charge. We just have the electric unit charge, and the same thing goes, and that's a bit for in general. We talk about color charges and flavors of quarks. I'm going like, give me their physical dimension. What is it? As for now, they appear to be in a matrix analysis, they appear to be some kind of, form factor or whatever. They help you to make sense of stuff mathematically, but, they don't come with a physical dimension. The last problem I have with Yukawa's invention of that new nuclear charge is that you really have people talk about the fine-tuning problem and why are the nature's constant exactly what they are, so precisely tuned one to another. But well, here we have a problem that as soon as there's sort of a slight deviation from that range parameter in the distance between those two nuclear charges or whatever you want to call them, well, either the electrostatic force will take over and push them away, or else the nuclear forces will be stronger than the electrostatic force and make these two charges sit right on top of each other. So it's like that problem of how can an atom exist because it would radiate its energy away. Well, this is a problem that is a lot worse. It just is not a stable equilibrium situation, even if that situation would work. What I did in my papers and other papers where I sort of revisited that problem after this year inspired me to do a lot of other stuff is actually say like, okay, if you need a force law that obeys the energy conservation law, that falls off with the inverse square law. Well, it's not in this paper. Oh, I don't have it here at the moment, I think. Well, you could think of a 1 over r. Yeah, I do that further here. Where? Or maybe not here, but you can think of indeed a sort of a dipole field, and that will make it come around. The problem is that yeah, it won't be a symmetric solution. But yeah, that would work. And then you have different potentials, but based on electromagnetism and the assumption, crucially, that the neutron acts as a sort of a glue between two protons and consists of some kind of dynamic combination of positive and negative charge. And then you have, you have a sort of a three-body problem. Two protons, two positive charges, and then yeah, well, a four-body problem, then a positive and a negative charge in the neutron, and that's sort of where probably these I mean, this model of Yukawa is also very static. Huh? It doesn't think of matter particles or nuclear the things in the nucleus as a sort of dynamic. Charged oscillations. It's a charge that is in motion constantly. No, it's just like a point-like thing that is associated with nuclear charge in this case, and that's sort of the whole problem of what I think of quantum chromodynamics or high energy physics is that they fall in that trap of thinking very statically. So I'm gonna end my lecture with maybe quoting from this gauge theories. You can look at it on page 16, 17 in the 4th edition, where then, from this very shabby, short, half-page analysis and presentation of this formula, the immediately jump on, yeah, we would have a force, then a nuclear force that, how would it work? It works by, the emission and absorption of a U minus quantum, and of course there's the antiparticle of that too, U plus quarticle, and so these are virtual quantums. Quarks hadn't been invented, and or gluons hadn't been invented at that time. So, but that's sort of the equivalent of a gluon, a U minus or a U plus quantum, and Aitchison and Hayes, they recognize it. These are Hall transitions and emissions, absorptions, and he writes it's an energy violating transition. Such an energy violating transition is known as a virtual transition in quantum mechanics. Such transitions are routinely present in quantum mechanical time-dependent perturbation theory and can be understood in terms of the energy-time uncertainty relation. Frankly, I switch off, and then it goes on. He presents these Feynman diagrams, which probably are useful in a lot of situations. But here's sort of how a neutron and a proton stay together. There is actually in the diagram, now that I see it, a bit of a Platzwechsel idea that Schrödinger had, where a U minus quantum goes away from a neutron, and the neutron becomes a proton, and then it goes to the proton, gets absorbed there, and the proton becomes a neutron. I'm just going like, why don't you replace that U minus quantum by, a negative unit charge, and think of the neutron as the glue that holds that neutron and proton together. I'll leave it at that. I bought the books. They're quite expensive. These gauge, these textbooks of QCT and gauge theories and high energy physics. But yeah, I find them. It's called a practical introduction. Also, there's hardly any references to practical experiments in these books. Also, and that's something that is rather shocking to note. In any case, I'll leave it at that. It's a bit of a rant. I realize, rather than a rant, it's really what is left to do for me. I said I'm on ResearchGate here. My stats are going really well. Let me go home. And I showed up sort of have now 342 points in just 1 or 2 years. So yeah, what's left for me to do is encourage you to read this. This is open research from someone who does not have a PhD in physics, but I do have a lot of other degrees, including postdoc in economics, and I work as a computer scientist. And I want to see my score in this field go up because I'm a bit arrogant there. Then or is it here, quantum physics? I want to see it go to the top 20%. That's my goal for the coming years, by exactly saying like I think I wrote what needs to be written. I probably need to package it in a bit in a book, but things can be demystified. These are my computer scribblings. But yeah, these mystery series that I wrote, 101, 102, 103, 104, I really give you some tools and models. Indeed, think in terms of the proton and neutron and the electron having a structure, being dynamic charged oscillations. And then you can see that a lot of the mysteries don't seem to be mysteries. The way an electron goes through one slit or two slits. The one photon Mach-Zehnder experiment is the same thing. The proton yarn ball puzzle, as I call it. These models give if you think of a proton as a three-dimensional oscillation of a positive charge spinning around, sort of a spherical model, then you get the radius, but did we solve do we have the exact trajectory? No, we don't. But it's clearly much less of a mystery than just saying like, oh, what explains the proton radius? Well, very easy formulas. Have a look at it. Here it's sort of mystery 101, these intermediate vector bosons. That's actually what I talked a little bit about. These models where quantum field theory, where you have virtual particles ferrying momentum and energy around. You really go like, honestly, that's medieval. Do we really think so? We have some kind of virtual particle, and then that carries the energy from this place to that place, or carries momentum from that place. And then what happens to that particle once it has done, it has emptied its load of energy or momentum? The virtual particle disappears, or is it at energy? This quantization of energy and momentum, that I believe, and these fields, and there are charges, they're discrete things in nature, but these virtual particle theory is just like a very mechanistic, old-fashioned view of how forces actually work. We don't need, to push against the wall to make that wall move, I would say. I mean, at the micro scale, it's really, electromagnetism is not a contact force, etc., etc. Have a look and see if it makes sense. If not, of course, then well, it doesn't make sense. Okay, I wish you a great day, and that will be it